Uh, in a two dimensions, wavefront is a line on which the disturbance has the same phase at all points. Suppose we have this kind of waves, and we consider this as a wavefront. We can, but this wavefront is an imaginary line, or a imaginary positions, which is from which the every wave has a same phase. This phase, this phase, and this phase. All the crust has been considered here. Similarly, all the trough can also be considered. But in that case, if one trough is considered, then all the trough should be considered. No crust will be considered in that case. So in this way, wavefronts are produced. A wavefront is a line, is an imaginary line. It's not any line, but it's an imaginary line, just in our mind. So on which the disturbance has the same phase at all points. The crust of wave in a ripple tank can be thought of, can be imagined as a wavefront. A vibrating source produces a succession of wavefronts at the same phase. A vibrating source produces a succession of wavefronts wavefronts all of the same shape. So a ripple tank, straight wavefronts are produced by a vibrating bar, a line source, and a circular wavefronts are produced by a vibrating ball or a point source. Suppose we have a ball or a bar. So if we use this bar, we can produce straight line wavefronts. By using this, we produce the circular type of wavefronts. At every crust we have this circular shape. So this is, all the crusts have been shown. So this is wavefronts, and wave will be like this. So in case of circular waves, a circular disturbance, circular waves are produced in a ripple tank from a point source or a vibrating bar, a line source. It's straight line wavefronts are produced. So a line drawn at right angles to a wavefront which shows its direction of travel. Suppose this is wavefronts, and the direction of wave travel is called a ray. So if this is wavefronts, and this is the incident wave, and this is the reflected waves. So straight wavefronts and corresponding rays are shown in figure 3.17. The properties of wave reflected at a plane surface, refraction and diffraction, can be illustrated by the behavior of water waves in a ripple tank. So this wave has all the properties: reflection, refraction, and diffractions. And we will see that when wave produce a reflection, and when produce refraction and diffraction, we will discuss in this. Wave reflected at a plane surface, so can be illustrated by the behavior of water waves in a ripple tank. It shows that the angle of incident and the angle of reflections are always equal. So this is the angle of incident with the normal. So this is the angle of a reflection with the normal. So this is normal, is a perpendicular line to the surface. So this is the surface, and a perpendicular line is this, and incident wave are available here, is acting here on this normal, and it is reflected with this. And these are the wavefronts, where these are the crust points or a trough point or any other point, but it's imaginary points of the wave of having all the same phase, all in same phase. So this is called reflection of waves. Now refraction: if a glass plate is placed on a ripple tank like this, a glass plate is placed on a ripple tank, so that the water over the glass plate is about 1 mm deep, but in a 5 mm deep elsewhere. So if we place this glass slab in the ripple tank, so 1 mm deep, but in 5 mm deep elsewhere, The continuous straight wave in the shallow regions are found to have a shorter wavelength. Here in this region, the wave will have a shorter wavelength than those in the deeper part. So if this is a deeper part, this is a shallower part, the wavefronts are closer together. So in this region, the wavelength will be shorter, so the wavefront will be closer. The crust will come closer in this region. So both sides of waves have the frequency of vibrating bar, and since V is equal to F lambda, if F lambda has decreased, so has V. Since F is fixed, since the frequency is not changing and lambda has decreased, so the velocity will decrease. So in a refraction, the velocity always decreases. Hence the wave travels more slowly in a shallow water. In a shallow water, the waves travel so slowly. When the plate is at an angle of to the wave, the direction of the travel in the shallow region is bent toward the normal. So when the plate is at an angle to the waves like this is in an angular position, then the direction of travel in the shallow region is bent toward the normal. So in this case, here we have a deep water and the angle of incidence is this. This is the normal line, and here in a shallow water, this bent toward the normal. So in this region, this wavefront has a gap is larger. Here the gap is closer, so the gap is smaller. So we can see this, and this is because of the refraction of waves in a shallow water. Here we have a deep water, here we have a shallow water. Due to this shallow water region, the wavelength decreases and speed decreases, while in this region the speed is faster and the wavelength is larger. So the change in the direction of the travel of the wave, which occurs when their speed and hence wavelength changes, is termed refraction. The change in the direction of the travel of the wave. The change in the direction of the travel of the wave, which occurs when their speed and hence wavelength changes. Speed changes, wavelength changes, and this phenomena is a refraction of waves. Refraction. So the speed of waves also changes, and refraction occurs when wave moves from one medium to another. Here this medium is different, this medium is different, because here the water is deep. Here we have placed some objects inside the shallow water, where so this depth of water has decreased and the wave shape changes. So for example, the light waves are refracted when they move from air to glass. This refraction phenomena also occurs in lights. So this is refraction. Another phenomena is diffraction, which